Welcome to Golang for Devs, the series where I teach you everything Go as directly and quickly as possible. Today, I'm covering the basics of concurrency. This is a heavier one, so if you want to follow along, the link to the code is in the description. We'll start with Go routines using some super simple examples. First, a Go routine is just a function that you can run concurrently with other code. You can think of it like a thread in other languages, just lighter weight and managed by the Go runtime. All of your code in Go will run inside of a Go routine. So when you start up a Go program, the main function will execute in an initial Go routine that's spawned by the Go runtime. And this is called the main Go routine. But it's super easy to make your own Go routines as well. So let's say I have a function called count that prints from 1 to 1000. If I call the function normally, it will execute synchronously in the same Go routine we're already in. So these lines will execute in the main Go routine. So if I run this code, it will print 1 to 1000 and then print done. But if I use the Go keyword to call the count function, it will execute concurrently in a newly spawned Go routine. And that's how you use concurrency in Go. Very easy, definitely no hidden complexities here, no. But when I run this program, all we get is done. We don't get any numbers printed out. So what's going on? So when you run Go count, it's executed in a new Go routine that's run concurrently with the Go routine we are in, which again is the main Go routine. But after count is called, the main Go routine will just continue executing and move to the next step, which is printing done. So that executes before the new Go routine we spawned is able to print any of the numbers. Now the key point here is when you hit the end of the main function, the Go program will just exit and kill any Go routines that may still be doing work. Meaning in this example, you can't rely on the output to actually print any numbers because the result will be non-deterministic. So how do we solve this? The best way is to use the WaitGroup type from the sync package in the standard library. And I'll leave links to the documentation in the description. A WaitGroup is basically just a counter that lets you pause Go routines until the counter hits 0. You need to add and subtract from the counter yourself, but when you instantiate it, the counter will start at 0. Then before you call count in a new Go routine, you can use WaitGroup.Add to add 1 to the counter. So that's one new Go routine running. And before we finish the main function, we can call WaitGroup.Wait. So this wait will pause the main function's execution until the counter hits 0. So now the program won't exit because the main Go routine will be blocked until the WaitGroup's counter hits 0. But we still need to decrement the counter ourselves to tell the WaitGroup when to unblock. And to do that, the count function needs to accept a WaitGroup as an argument. And then at the top of the function, we can call defer WaitGroup.Done. And all done does is decrement the counter by 1. So once this function finishes execution, the defer function will call, which will unblock the WaitGroup and let the main function finish execution. An important rule here is after you start using a WaitGroup, you can't copy the value. So it needs to be passed into the count function as a pointer. Because if you passed in the actual value, the function will receive a copy of the WaitGroup, and then calling done on that wouldn't do anything to affect the original WaitGroup. So now if we run this code, the count function will run in a separate Go routine, and the main function will wait until the count function is finished before it completes execution. So you get all the numbers like you expect. If you're an async await kind of dev, you can think of running Go routines as running asynchronous code without the waiting part. And then if you need to wait, you add your own wait logic on top of it. So everything works now, but there are a couple ways we can clean this up. First, instead of passing the WaitGroup into count directly, we can wrap the call to the count function in an anonymous function, and then call WaitGroup.Done in that function. And just to make this clear, we define a function here and then execute it using Go in a new Go routine with the brackets at the end. You'll see this pattern a ton, so it's good to get it fully ingrained in you. I have to get rid of this. And then when we run this, we get the same results, just a little bit cleaner syntax. Next, since Go 1.25, there is an even easier way to do this. So instead of doing add and done manually, we will replace all of that with WaitGroup.Go and then pass in the count function. So this helper will automatically increment the counter when the function is called and decrement it when the function is done execution. And again, running this should get us the exact same results as before. So that's wait groups. They are a fundamental building block of concurrency in Go, so they're important to understand. And before we move on, if you've made it this far, hopefully you're finding the video helpful. There's way too much Go concurrency content to cover in just this video. So consider giving it a like and subscribing so you don't miss out on future videos. All right, the next important building block for concurrency in Go is channels. And you can think of channels like pipes that you can send messages through between two different Go routines. Okay, you create a channel using the built-in make function. So this is a channel that can send and receive int values. Specifically, this is an unbuffered channel, meaning when you send values to the channel, it has no means of queuing up those values. It will make a lot more sense in a bit when I go over buffered channels. So you can send a value to a channel using an arrow syntax like this. And you can receive a value from a channel using the same arrow syntax, but just coming out the other side of the variable. Something that tripped me up when I was first learning Go is that these arrows can only point left. So you can't do something like this to send a value to a channel. So in this example, we are sending the value of 10 to the channel and then receiving it in value, and then I will print the value. But if I run this, we get a deadlock error. This brings us to the first important point about channels. When you send to a channel or receive from a channel, it's a blocking operation. So when we send the value of 10 to the channel here, the main Go routine will be blocked until something receives that value on the other side. But if execution pauses at the send operation, we'll never make it to the receive operation, so we hit deadlock. Okay, so let's do a more full example that actually works. So let's say I have a function called generate that accepts a channel. And the arrow syntax inside the function definition just means that this channel in the function is a send-only channel. So the arrow points into the chan keyword. So we are only allowed to send data into the channel, not receive data from the channel. So this function will generate a total of 5 random numbers and send them to the channel. And in between each one, we're going to sleep 500 milliseconds. This function should be run in a new Go routine. So we're going to need a wait group and the actual channel to pass in. And then we can use WaitGroup.Go to execute the generate function in a new Go routine. Now let's say we have another function called transform that accepts the same channel as an argument, but this time it is a receive only channel. So inside this function, this arrow heading out of the chan keyword means we're only allowed to pull data out of the channel. And this function should continuously receive values from the channel, modify those values, and then we'll print them. Then in the main function, we can spin up another Go routine to execute the transform function. And don't forget to use WaitGroup.Wait, or the main Go routine will exit before your other Go routines do anything. And I made a little mistake here, but if we run this, we'll get 5 outputs, and then we'll hit another deadlock. So what's going on? We still have one more thing to fix. First, once the generate function is finished sending values into the channel, we need to close the channel. And we can do this using defer with the built-in close function that Go gives you. So after this function completes, the deferred call will get executed and the channel will be closed. One important point here is that the function or Go routine that is responsible for sending data to a channel should always be the one to close a channel because it knows when there's no more data to send. Okay, next in the transform function, we need to check if the channel is closed. And if the channel is closed, then we need to exit the function and exit the Go routine. First, you need to add an OK variable to the channel receiving command. Then, if OK is false, it means the channel is closed and it's empty, so it doesn't have any more values coming through. And when the channel closes, we can print channel closed and break from our loop, which will exit the function. So now if I run this example, we should get the 5 values as outputs, and then everything closes correctly with no deadlock. And congrats, you've built your very first data processing pipeline in Go. Fun stuff. All right, there is one more feature that can make the transform function look a lot nicer. So instead of having our own infinite for loop and manually checking if the channel is closed, we're just going to use a for range loop instead, where we range over the channel. And we'll do the same operations, and you're good to go. So when you use a range loop over a channel in Go, the loop will automatically exit once the channel is closed. So there's no need to manually check for the channel closing. All right, I'm going to cover patterns you can use with concurrency in Go in future videos, but I wanted to show you a simple worker pattern here to illustrate some of the stuff you can do with channels. So let's imagine the generate function is super fast. So there's no sleeping, and we'll up the number of numbers it produces. And imagine the transform function was very slow and CPU intensive. To illustrate that, we'll sleep every time we process a value from the generator. And to give it some variance, we have a random duration that will sleep each time. And I'll put a print line in here so you can see when we are processing data. And if I run this code, you can see that the transform function is the rate limiting step that's slowing everything down. So to speed this up, we do what Go does best, which is run many transform functions concurrently. So instead of spinning up one Go routine that is running the transform function, we're going to run 10. So it's super simple. In a loop, we just go over it 10 times and spin up a new Go routine each time. So now we have 10 Go routines, all running the transform function. And if there are multiple cores available, the Go runtime may run these in parallel as well. So each time the generate function sends a number to the channel, one of the instances of our transform function will pick up that value. And the cool part here is that even though we're receiving from the channel in 10 different concurrently running functions, each value that's sent in is only ever processed once. So channels act less like a broadcast system and more like a queue in that way. And now if I run the example, you can see that the multiple transform functions are able to process everything super, super fast. Okay, next up, I want to go over buffered channels. So a buffered channel is the same as an unbuffered channel, but it has capacity to store values in a queue. To start off, let's imagine our generate function is streaming data in from an external data source, and the data source has inherently bursty traffic. So I'll up this to 1,000. And then we'll 10x the amount of data sent to the channel on every iteration. And then on each iteration, we'll add a sleep backend for 3 seconds. So now every 3 seconds, we're producing 10 numbers and sending them into the channel. Let me also add a print line here so you can see when data is coming in. I will also remove the concurrent transforms and put it back to a single transform function. So our channel is still an unbuffered channel. So when I run the example, every time we get data from the generator, the transform function needs to process it before the next piece of data can come through. So it ends up being super slow. But if the data is coming in large bursts, ideally, you would want some capacity to absorb those bursts while waiting for the transform function to do its thing. So this is where buffering the channel comes in. Super easy. You just need to add a second argument to the make function. So in this case, we have a channel that has a capacity of 25 for the queue of values it can store. So the advantage of this is when you send data to the channel is able to queue up that data. So this line doesn't need to block and wait for a receiver to receive the value. So we're able to produce 10 values, populate the channel very quickly, and then the transform function can pick them off one by one. Now, if the channel fills all the way up, then it will start behaving like an unbuffered channel again. So sending data into the channel will be a blocking operation. And now if I run the code again, you can see we get bursts of data, and then the transform function starts processing. And you can imagine if the generate function is streaming data from an external source and you don't have a capacity to buffer what comes in, then this operation will always pause the generate go routine and you might miss data points. But again, if the channel fills up to capacity, then this will start blocking again and you still might miss data points. So you need to tune it properly to whatever you're doing. So using concurrent workers lets you process data a lot faster by running multiple data processing functions concurrently. And using buffered channels gives you a queue that can absorb bursty traffic. And those two features together make Go routines and Go channels a super powerful tool to handle multiple HTTP requests at the same time, or to handle a data processing pipeline like this example. Okay, the last big building block of concurrency in Go I want to cover is contexts. You may have noticed that using a finite loop to generate values doesn't really reflect how a real service would stream data in. So let's replace all this with an infinite loop. But if this is running infinitely, we need some way for the Go routine to know when to shut down and when resources need to be cleaned up. This is where contexts come in. A context is an interface defined in the context package of the standard library. And again, I'll leave a link to the docs in the description. You can use contexts to do 3 things. First, you can use them to send cancellation messages to multiple Go routines at the same time. Next, you can use them to time out a Go routine after a certain amount of time has passed. And lastly, you can use them to pass request specific information, so like a request ID, into multiple Go routines. So to actually use them, you first create a context using the context.background function. And this will create just an empty context. Next, if you want a context that can cancel, we call context.WithCancel. And you need to pass in a parent context here. So this returns a new context and a cancel function that you can call that will send a cancellation signal to the context. So next, we can create a context with a value using, you guessed it, context.WithValue. And again, we pass in the parent context. But this time we're going to pass in a key and a value for that key. I will note that instead of using a string for the key, it's usually best to use a custom type with an actual instance of that type as the actual key. So instead of using the string, we're just going to pass in the request ID key. And you do that because contexts get passed between packages a lot. And if you use strings, there's a chance you might collide with keys that other packages use, which would be no bueno. And another important point here is that the context with the value is considered a child of the context with the cancel function because we passed it in as the parent. And that matters because when you cancel a parent context, all of its children will also be canceled. So you can stack contexts under a cancellation context and then cancel them all at once. So we'll leave the same Go routines we've been using, but I'm going to register a function that will cancel the context after 3 seconds has passed. Then we need to actually react to the cancellation signal when it comes through the context. So we have to pass the context into the generate function. And it's convention to use the first argument in the function as the context value that you're passing in. So next we need to use something called a select statement. So let's walk through this slowly. A select statement is just a fancy switch statement that is used to wait on multiple Go routines at once. So instead of running cases based on Boolean checks, it will wait for the first channel to be unblocked and then run that case. So here we call context.done, which returns a channel that's internally managed by the context. And when you call cancel on the context, the done channel is closed. So similar to how we checked for a closed channel earlier, where we had a value and OK, when the done channel closes, it will unblock and send. We're just not storing those values. So then this case will run. So when the context is canceled, we run any cleanup that we need to in the Go routine. In this case, I'm just logging a message with the request ID. And then we close the channel and return to exit from the Go routine. Now, if the context hasn't been canceled yet, this case won't be triggered. So then we go to the next case. And here we are waiting until the channel can receive a value. And as soon as it receives a value, we can run this case, which has no code because all we really care about is sending the value to the channel, which happens in the case check itself. And if you think this indenting syntax looks horrible, you are 100% right. And you just need to learn to deal with it because that's how it is. So we'll get rid of the close up here because we're closing the channel when the context is canceled. So our generate function should cancel after 3 seconds, and then everything should shut down gracefully. So if we run this, it should run for 3 seconds and then shut down. Cool. So like I said earlier, one of the use cases with contexts is instead of calling cancel manually, you can set a timeout so the context gets automatically canceled after that time. So we'll go to the next example, and instead of using WithCancel, we'll use WithTimeout. And you still pass the parent context in, but then you need to also pass in a duration from the time package. So this context will cancel after 1 second. And you should note it still returns a cancel function, so you're still able to cancel it manually. And it's worth noting that it is best practice to call defer cancel with that cancel. We'll pass the new timeout context into the WithValue function. So when I run this example, it should only last for 1 second this time instead of the 3. And that was a little bit faster, if you can tell. So that's generally how you use contexts. But if you were streaming data in a real app, you wouldn't rely on a timeout to shut your Go routines down. So let's go to the last example I want to cover in this video, and that is using signal.NotifyContext to cancel your Go routines. So instead of using a timeout, we're going to use a function from the signal package of the standard library called NotifyContext. So similar to the other functions, you pass in a parent context, and then you need to pass in signals that this context will listen for to be canceled. So the first one we're using is os.interrupt, and that will fire when you hit Command C in the terminal. And then the second one is syscall.sigterm, which will be triggered when your process is terminated by your container runtime or orchestration system. And just like with the timeout context, it is best practice to defer calling stop here, which will cancel your contexts. Okay, so we pass in the new context to our context with value, remove this trigger for 3 seconds. So now when I run this, it will run until I hit Control-C, and then the Go routines will have a chance to clean up resources and exit gracefully. So I hit Control-C, and then cleanup happens. And those are the basics of concurrency in Go. To sum it all up, the 4 big components of concurrency in Go are Go routines, which lets you run code concurrently, wait groups, which let you wait for concurrent work to complete, Go channels, which lets you communicate between Go routines, and contexts, which help you control the life cycle of Go routines. This video got pretty long, and there's still a lot of concurrency stuff I want to cover. So be sure to subscribe and stay tuned for those future videos. As always, keep breathing, keep building, and I'll see you next time. Peace out.